Yes, so let us start our discussion about one more combinational circuit, which is known as a multiplexer. Okay, so what is this multiplexer? So basically, this multiplexer, it is a combinational circuit that has many data inputs and a single output. Okay, so depending upon the control or select inputs for a n input lines, we have log n base to select lines. Okay, so basically, the block diagram of your MUX will be looking like this. So this is your multiplexer, and this multiplexer will have 2 power n inputs. This multiplexer will basically having 2 power n inputs and only one output, and only one output. And how many select lines we are going to have? We are going to have n number of select lines. We are going to have n number of select lines. So this is nothing but our multiplexer. Okay, so yes. So basically, there are different type of multiplexers depending upon the value of n. So if the value of n is equal to 1, if the value of n is equal to 1, then the multiplexer it is known as 2 cross 1 multiplexer. And if n is equal to 2, then it is a 4 cross 1 multiplexer. And if n is equal to 3, it is a 8 cross 1. And if n is equal to 4, it is a 16 cross 1 multiplexer. Okay, so how many select lines will be there for this? The select lines will be equal to 1. Select lines will be equal to 1 for this, and in this case the select lines will be equal to 2. Select lines will be equal to 2, and in this case select lines will be equal to 3, and so on. And in this case select lines will be equal to 4. Okay, so depending upon the value of n, the select lines are nothing but the value of n, and coming to inputs, it is nothing but 2 power n. Okay, so this is how we are going to select our multiplexers. So let us start with the basic 2 cross 1 multiplexer, and let us try to understand how this multiplexer is working. Okay, so let us try to understand about 2 cross 1 multiplexer. So in a 2 cross 1 multiplexer, how many inputs we are going to have in a 2 cross 1 multiplexer? Basically, we are going to have two number of inputs and only one output, and only one output. And how many select lines we are going to have? So select lines will be equal to basically 1. Select lines will be equal to 1. So this is how we are going to decide how many inputs are there, how many outputs are there, and how many select lines are there. Okay, so first of all, let us draw the diagram of this 2 cross 1 multiplexer. So this is our 2 cross 1 multiplexer, and in some of the exams or in some of the books, you will have one more representation of this multiplexer like this. So this is also one more representation of multiplexer. In some of the exams you can see this. Okay, so these two are same. You can either represent with this or you can either represent with this. Okay, so how many inputs we have for a 2 cross 1 multiplexer? We have basically two inputs, 1 and 2. Okay, and we have two outputs, sorry, one select line and one output. Okay, here also we will have the same. So I will represent this first pin with I0 and second pin with I1. And this is my select line. So I will represent this with S0. Now, how this multiplexer is basically working. So this multiplexer will give your output as I0 if select line is equal to 0. That is, if select line is equal to 0, it is going to select your input first pin to your output. Okay, so basically this is going to select your input to Y if your select line is equal to 0. And if your select line is equal to 1, your I1 will be selected to the output. Depending upon the value of S0, your input value has been decided, whether which input value will be driven to the output. Okay, I will write down here. Depending upon value of select line, depending upon select line, output will be decided. Output will be decided. That is, S0 if it is equal to 0, then Y is equal to first input I0, and if S0 is equal to 1, your output will be equal to I1. So depending upon your select line, your output will be decided. So to which input the output should be connected, that is decided. Okay, so you can assume this as your switch also. So the multiplexer, it is basically acting like your basic switch. Okay, depending upon the value of your select line, it is going to assign your output. So let us try to draw the truth table for this. So this is select line S0, and this is I0, I1, and Y. So if the select line is equal to 0, I0 is equal to 0, I1 is equal to 0, and 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay. So if your select line is equal to 0, then your Y will be equal to 0. That is I0 will be given. I0 will be given at your output. Okay. And if your select line is equal to 0, then also I0 only is given. Okay. And if your select line is again 0, it is going to give in I0 only, and here also it is going to give I0 only. Okay. And next 1 0 0, 1 0 1, 1 1 0, 1 1 1. Okay, so here you are going to get I1 as your select lines. 0, that is I1 is being given, and here I1 is being given, I1 is being given. So you can reframe this truth table like this. So S0, I0, I1, Y. So if your select line is equal to 0, then whatever may be the value of I1, only the I0 will be given. So if I0 is equal to 0, Y is equal to 0. And if your select line is equal to 0, I0 is equal to 1, whatever may be the value of I1, only Y will be equal to I0. Similarly, vice versa, that is don't care, 0, 0, 1, don't care, 1, 1. So this is how your 2 cross 1 multiplexer is going to work. Okay, is it clear? Now from this truth table, let us try to write down the equation, output equation, that is Y will be equal to S0 bar into I0, S0 bar into I0 plus S0 into, where is this, where it is becoming 1? Yeah, here, S0 into I1. I'm not considering the don't case. I'm just writing by considering only the min terms. Okay. So output Y is equal to S0 bar into I0 plus S0 into I1. So this is my output expression for a 2 cross 1 MUX. This is also known as your Shannon's expression. So this is also known as your Shannon's expression. So this is how we are going to form the equation for your multiplexer. Y is equal to S0 bar into I0 plus S0 into I1. So you can also substitute the values, like let's say suppose if your S0 is equal to 0, then output Y, and let's say if your I0 is equal to 1 and I1 is equal to 0. Okay, then output Y will be equal to S0 bar is nothing but 1 into I0 is nothing but 1 plus S0 is equal to 0, so it will become 0. Okay, whatever may be the value, so Y will be equal to 1, that is nothing but I0. Okay, so this is how using this Shannon's expression we can write it. Now, so there is one more optional signal, that is enable signal. Okay, I will write down here. So multiplexer. Okay, so this is optional. So how can you write this multiplexer with enable signal? So this enable signal which we are taking is active high. That means if enable is equal to 1, then only multiplexer is going to work. Or else if enable is equal to 0, multiplexer it is not going to work. For example, if enable and what is your select line S0 and this is your output Y. Okay, so enable is equal to 0, whatever may be the value of S0, your output will be equal to don't care on, or your output will be equal to 0. Okay, and if your enable is equal to 1, if you are giving your select line is equal to 0, first pin I0 will be selected, and if your enable is equal to 1, then your S0 is equal to, it may be, if it is equal to 1, then your Y will be equal to I1. Okay, so using this enable pin, we can draw this truth table like this. Okay, So this enable signal, it is an active high signal. That is, if it is equal to 1, then only you are getting your output, or else you are not getting any output. And if you want to write down a Shannon's expression, your output y will be equal to enable into S naught bar into I naught plus S1 into, sorry, S naught into I1. So this is the Shannon's expression with your enable signal. This is active high. Next, so there will be active low enable signal also. Sometimes we will see this questions, this type of questions we will see in our problem solving sessions. I will show you. So if we have active low enable signal, your multiplexer equation will look like this: y is equal to enable bar into s naught into I naught, s naught bar into I naught plus s naught into I1. So this is your expression with your active low enable signal. And the diagrams for your active and the diagrams for your multiplexer with active high enable signal will look like this. So this is your multiplexer with two number of inputs as I naught and I1, and this is your output y, and this is your select line S naught, and here you are providing one more signal which is known as your enable. Okay, and this is active high. This is 2 cross 1 mux, and you have two inputs I naught and I1, and there will be enable bar. Okay, active low signal, select line y. Okay, so this is optional signal. If you want, you can use, or else it is optional, and by default its value will be equal to 1. Okay, yes. So let's discuss about one more type of multiplexer where your n value is equal to 2. If your n value is equal to 2, then we can form 4 cross 1 multiplexer. And for the 4 cross 1 multiplexer, the number of select lines will be equal to 2. Select lines will be equal to 2. Okay, now, so for this 4 cross 1 multiplexer, the number of select lines will be equal to 2. Next, so let's see the diagram for this. So you can draw like this. This is your 4 cross 1 mux with 4 number of inputs: I naught, I1, I2, I3, I naught, I1, I2, I3. These are the 4 pins, and this is your output y. And there will be two select lines, S naught and S1. Here S0 will be MSB and S1 will be LSB. Okay, or else you can reverse also, S1 and S0. Then this S1 will become MSB and this S0 will become LSB. Okay, here we should be somewhat careful. Now, so this is your 4 cross 1 multiplexer. Okay, and your 4 cross 1 multiplexer, coming to the truth table, S1, S0, output is Y. So 0 0, 0 1, 1 0, 1 1. So if S0 and S1 is or zeros, then your output will be equal to I0, and here it will be equal to I1. Here we are going to get I2, and here we are going to get I3. Depending upon the values of S1 and S0, you are going to get your outputs. And if you want to find out the expression for your output expression, then you can write y is equal to S1 bar S0 bar into I0 plus S1 bar S0 into I1 plus S1 S0 bar into I2 plus S1 S0 into I3. So this is the Shannon's expression for your 4 cross 1 multiplexer. So this is how we are going to draw your Shannon, derive your Shannon's expression. Yes. So is it clear? Any doubts or any queries up to here? Yeah. And by seeing this expression only, we can draw the logic diagram of your multiplexer. By seeing this logic expression only, we can draw. So I will draw here. So you can take your select line I0, I1. So this is your select line, and this is your I0, and this is your I1. And from here you can take your NOT gate. Okay, so S0 bar into I0 and S0 into I1 and S into I1. So this is your output y. Okay, so this is the logic diagram of your 2 cross 1 multiplexer. Same, by using this expression you can draw the logic diagram of your, by using the Shannon's expression you can draw the logic diagram of your 4 cross 1 multiplexer. Okay, and for n is equal to 3 it will become a 8 cross 1 multiplexer with 8 number of inputs and 3 number of select lines, and depending upon the value of your select lines you are going to get your output. Okay, I think there is no need to discuss that 8 cross 1 mux, that we are already clear. Okay, now for example, let's say if you have a multiplexer like this, which is a 4 cross 1 mux, and it is having two select lines S1 and S0, and it has the input pins as I3, I2, I1 and I0, and this is your output Y. Now if my S1 S0 is equal to, let's say this is 1 0 1 1, let's say this is 0. Okay, now my, if my S1 S0 is equal to 0 0, then can you tell me what is my value of Y? If my S1 S0 is equal to 0 0, I made my select lines to 0, then what is my output Y? If my select lines are equal to 0 0, then what is my output Y? No, so it is I0, which is equal to 0. So here we should be careful. So while solving the problems, this is a major confusion many will face. So here the notation is I3, I2, I1, I0. I0 is the first pin and I3 is the last pin. Okay, so if we are applying 0 0, so S0 S1 S0, if it is equal to 0 0, we are going to consider the I0 pin input. Okay, and if S0 and S1 are 1 1, we are going to consider the I3 pin input. Okay, this we should be careful. Yeah, so while solving the problems also, they might reverse the order, so this we should be careful, and we should do the problems. Okay, so while doing the problems I will show you. Yeah, so this is about your 2 cross 1 mux, 4 cross 1 mux, and so on, 8 cross 1, 16 cross 1. By taking the value of n, we can decide the type of multiplexer which we are getting. Okay, now let us try to design all the logic gates using the multiplexers. So these multiplexers are basically, these are your universal gates. Multiplexers is an universal gate. That is, you can use this multiplexer to build any logic gates. Okay, so how to represent? Let us start with your basic NOT gate. Okay, so this is your NOT gate with input A and output as A bar. Now how to design your how to design your NOT gate using a multiplexer? So there are basically two ways. Okay, there are two approaches for implementing your logic gates using the multiplexer. Okay, first approach, so approach one is use the Shannon's expression. So how to use this Shannon's expression? So we know already y is equal to s bar into I naught plus s into I1, and NOT gate using 2 cross 1 mux is our question. NOT gate using 2 cross 1 mux. Okay, so this is our expression now. So I can simply substitute s is equal to a, and I1 is equal to 0, and I0 is equal to 1. Okay, if I substitute this, then my output will become y is equal to a bar into 1 plus a into 0. That means my y will be equal to a bar. So I'm getting my y is equal to a bar. If I substitute my s is equal to a, and if I provide I1 is equal to 0 and I0 is equal to 1. Okay, so I can simply write down like I can draw the multiplexer like this. So this is my mux, and this is I0, and this is I1, and this is my select line. Okay, and here I am providing value a, and or else you can provide 1 also. Okay, here I am providing 1, and here I am providing 0, and here I am providing a. Okay, so this is y is equal to a bar. So this is how we can design our multiplexer 2 cross 1 not gate using 2 cross 1 mux using the approach one. Okay. Now in approach 2, what we can do is we can take the help of our truth table. We can use the truth table of logic gate. So what is this approach? Let us try to understand what is this approach. So we can just take the help of our truth table of the NOT gate. So the NOT gate truth table will look like this. So this is our input A and output. So we have only two possible combinations, 0 and 1. So we'll get 1 and here we are going to get 0. Okay. Now, so how to analyze this? Any idea? So by seeing this truth table, how to analyze this? So we can simply see your output. This you can connect your select line. This A you can connect it with your select line, and this output. If you see, if your select line is equal to 0, you are going to get 1 as your output. That is, you are going to get I naught is equal to 1. And here, if your select line is equal to 1, you are getting your output as 0. That is, you are getting I1 because your select line is equal to 1. So by this, you can decide the values of I naught and I1. I naught is equal to 0, I naught is equal to 1, and I1 is equal to 0. From this also, you can draw the diagram of your multiplexer. This is I naught and this is I1. You're connecting 1, 0, and you're going to get your output Y. Yes, is it clear? Now, so you can follow any approach. Basically, I feel approach 2 is easier. Okay, approach 2 will be somewhat easier and simple. So if you wish, you can follow any approach. Okay. So let us try to build our next type of gate, which is AND gate using 2 cross 1 mux. So how to build this AND gate using 2 cross 1 mux? Again, I am following approach 2, where this AND gate it is going to have two number of inputs A and B, and your output Y will be equal to A dot B. So this is your AND gate now. So I'm basically drawing the truth table of this A, B, Y. 0 0 0 1 1 0 and 1 1. So 0 0 output is 0 0 0 and 1. So this is, I only have one select line. Okay, I only have one select line. So this select line you can connect either A or you can connect B. Okay, I'm connecting A. Okay, and I have two inputs. Okay, now which input should connect? Let us decide. Okay, now if we see, I have connected my select line to A. I have connected my select line to A. Now if my select line is equal to 0, at my output I am getting the value of B. Okay, and if select line is equal to 0, at the output I am just simply getting 0. Okay, so if select line is equal to 0, whatever may be the value of B, if select line is equal to 0, whatever may be the value of B, your output is 0 only. Okay, so that means my I naught value is equal to 0 because my select line is equal to 0 now. That is, I am getting my I naught and the value of I naught is equal to 0 since my output is constantly 0. Okay, so this is my I naught and I am going to connect 0 at the first pin. Now, if my select line is equal to 1, value of B is equal to 0, I am getting Y is equal to 0. And if my select line is equal to 1, value of B is equal to 1, I am getting as 1. That means my value of I1 is equal to B. So whatever the value of B, I am getting at the output, that is I1 is equal to B. So this is my I1. Sorry, this is my B. And this is I1. This is Y. So this is how we are going to implement a AND gate using a 2 cross 1 multiplexer. Yes, is it clear? AND gate using 2 cross 1 mux. Inputs are 0 comma B. Exactly, correct. Okay. Next, try for OR gate also. Try and tell me what are the inputs, what are the select lines. And this is A, B, Y. 0 0 0 1 1 0 1 1. So 0 0 0 1 1 1. Okay, so if you see, if you connect this as select line and this is one of the pin here, if the select line is equal to 0, you are getting your output B. So I naught is equal to B, and here we are getting I1 is equal to 1. Okay, so this is my multiplexer with the select line as A and one of the input as B and another input as 1. This is I naught and this is I1. And this is my output y is equal to a plus b. Are you getting the same thing? Exactly, b and 1. Okay. Now, what is next gate? And or NAND. Okay. So let us try this NAND gate. So tell me how to build this NAND gate. So this is your NAND gate. A B y is equal to a b bar. Okay. So let us write the truth table for this y a b and y 0 0 0 1 1 0 1 1 1 1 and 0. So if you can see, if your select line is this is your select line, if it is equal to 0, s is equal to 0, you are getting your output as y is equal to 1. Okay. And if select line is equal to 1, you are getting complemented value of b. Okay. That is y is equal to b bar. Is it correct? Exactly. Now, how to implement this B bar? For implementing this B bar, we need one more multiplexer which is acting as a NOT gate. Okay, so this is our multiplexer B, and here we are going to apply 1, and here we are going to apply 0. This is our B bar, and this B bar is given to the second pin of our multiplexer, and the select line of this multiplexer is A, and the first pin is being connected to 1 and the second pin is being connected to B bar, and this is our output y is equal to AB whole bar. Okay, yes. Next, what are the inputs and what are the select lines for NOR gate? Try for NOR gate also. Fifth one is our NOR gate. So NOR gate will look like this: A B A plus B whole bar. I will draw the truth table: 0 0 0 1 1 0 1 1. 0 0 is 1 and 0 0 0. Okay, so this is your NOR gate. Now, so coming to this, s is equal this, let's say this is E is s, so s is equal to 0 and here s is equal to 1. Okay, now if s is equal to 0, what are we having? So if s is equal to 0, we are getting the complemented version, that is b bar, and here we are getting 0. This is your y. In this case, y is equal to 0. Exactly. Okay, so again I need two multiplexers, b1 0 b bar. This b bar is connected to the first pin of your multiplexer, where this is your select line, and one more pin is 0, and this is y is equal to a plus b bar. Exactly. Okay, next, coming to XOR gate, try for XOR gate also. So this is your XOR gate. The symbol of your XOR gate, two input XOR gate, is this: A B, y is equal to A XOR B. Let me draw the truth table for this: A B y 0 0 0 1 1 0 and 1 1. This will be equal to 0 1 1 and 0, and this is your select line. S is your select line. Here we are having s is equal to 0 and we are having s is equal to 1. Now if s is equal to 0, you are getting the same output, that is y is equal to b, and if s is equal to 1, you are getting complemented output of b, that is b bar. So your inputs are b and b bar. Exactly. So I can take a multiplexer like this: b 1 0 b bar, and this b is given to this multiplexer. This is I naught and this is I1 and this is A. Okay, here we are getting A XOR with B. Exactly. Now coming to XNOR gate, how to implement this XNOR gate? And this is seventh gate. XNOR gate. So for the XNOR gate, this is your XNOR gate symbol, A B, Y is equal to A XNOR with B, and the truth table will look like this: Y A B 0 0 0 1 1 0 and 1 1 1 0 0 1. And if S is equal to 0, S is equal to 1. If S is equal to 0, you are getting complemented output of your B, complemented version of your B, and here you are getting same B, B bar and B. So these are your inputs exactly. So you can implement your B bar. This is your B and 1 and 0. Here you are going to get B bar. This you are going to give at the first input, and this is your A and this is your B. Y is equal to A XNOR with B. Exactly. So this is how we are going to implement all the logic gates using the multiplexer. Now, how to implement your logic gates using 4x1 MUX? Let us see them quickly. So let's see this simple NOT gate. Using 4x1. So this is your NOT multiplexer with two number of select lines, S1 and S0. Okay, and you have four number of inputs: I0, I1, I2, I3. I0, I1, I2, I3. And this is your output Y. Now, what should I do to convert this into a NOT gate? What should be my values of S1, S0, I0, I1, I2, I3? S1 value, S0 value, I0 value, I1, I2, and I3 values. What should be these values? Okay, so you can just simply take the Shannon's expression if you want. Okay, so what is the Shannon's expression? S1 bar S0 bar into I0 plus S1 bar S0 into I1 plus S1 S0 bar into I2 plus S0 S1 into I3. Okay, now if you take S0 is equal to 1 and S1 is equal to 1, okay, then you are going to get your input as I3. Okay, but what is your requirement? You need your A bar complemented of A. So what I'm going to do is I'm going to apply S1 is equal sorry, I'm going to apply S0 is equal to A. Okay, I'm going to apply S0 is equal to A, and S1 is equal to S1 is equal to 0, and I1, I2, I3 is also 0. So what I'm doing is I'm basically applying 1 0 0 0, and this is also 0 and this is 1. So substitute this and let me know, are you getting the NOT gate? Here I am applying E. Okay, this is 0 and this is E, and this is 1, and remaining all are 0. Then I will get simply E bar. So you can substitute here. So what is you are getting? So S1 is equal to 0 means it will become 1, and S0 bar is E bar, I0 is 1. So here you are going to get E bar plus S1 is 0, but I1 is 0. Okay, so this will become 0, and I2 is 0 and I3 is 0. So you are going to get E bar. Okay, is it clear now? So this is how you are going to implement a NOT gate using your 4x1 multiplexer. Okay, this is one approach. This is one approach, and there is one more approach also for this. What is that approach? So you can take the help of truth table and find out the minterms and take minterms. So how to take minterms from the truth table that we already know? So let's see. So this is our truth table A, and this is your output Y. Okay, if A is equal to 0, output is equal to 1, and if it is equal to 1, it is equal to 0. Okay, so what is the minterm which we are having? Only single minterm, which is M0. Okay, that minterm you are making to 1 here and remaining all minterms to 0. That's it. Just you are activating the 0th pin, that is I naught pin, as 1, and remaining pins as 0. That's it. Okay. Is it clear? Yes. Now let us try to implement your AND gate using 4 cross 1 mux also. So AND using 4 cross 1. So I'm following the second method. Okay. So what is the second approach? Just take the truth table for this. So the truth table will look like this: A, B, and Y. 0 0 0 1 1 0 1 1. 0 0 0 1. What is the minterm we are getting? M3. Okay. So what you're going to do, you're going to just draw a 4 cross 1 mux with select lines S0 and S1. Okay. And you're going to take your inputs all to 0 and just activate the third minterm I3. Just provide 1. And this is your A and B. You're going to get your output Y is equal to A dot B. Okay. Yes. Next, how to implement your OR gate? You can take again follow the same method. OR gate using 4 cross 1. So you can follow the minterms method. So A, B, and Y. 0 0 0 1 1 0 1 1. So this is 0 1 1 1. Okay. So we have minterms sigma m 1 2 and 3. Okay, and remaining we will keep it as 0. So this is your A and this is your B, and we are applying this as 0 1 1 1. You can substitute in the equation also, we'll get this A plus B. Okay, so it is this is A bar B plus AB bar plus AB. So you can take the common, that will become A bar B, plus if you take A as common, then you will get A, and this is nothing but A plus B. Is it clear how we are implementing this OR gate using 4 cross 1 mux? Yes. So this is how we can implement all the other logic gates also, like if we have XOR gate or NAND gate, okay, or any other gates if we are having, we can implement this basic logic gates using the higher order mux. Like if we say, let's say suppose if we have 8 cross 1 mux, then also we are going to follow the same method only. Okay, so this is how we are going to implement all the logic gates using 2 cross 1 mux, 4 cross 1 mux, and any multiplexer we are having. Okay, yes. So that's all about this session. So if you have any doubts or any queries, you can stay and discuss with me, or else you can leave the session. Okay, thank you. In our next session, we are going to discuss higher order mux using lower order mux, and we are also going to discuss how to implement any boolean expression which is given to us, like any random minterms which we are given. So how to implement that using the multiplexer. Okay, yes. Thank you.